Hello everyone. In today's lecture, we are going to discuss about programmable silicon photonics. So far, we have discussed important passive components, and also we have discussed how phase shifters can be integrated, particularly thermo-optic phase shifters to reconfigure certain components and circuits. And next level is we can have some photonic circuit defined in silicon photonics technology platform that can be programmed for multi-purpose for various different functions. Same circuit can be reconfigured for other type of applications. So, towards that, first what we are going to discuss universal 2x2 optical gate. Sometimes it is called tunable basic unit. So, this is actually it is just similar to any electronic gate. We will be trying to present one component device, specific device, which can be programmed for gate operation, optical gate. So, keep in mind that when we say optical gate, basically it is not like like for digital operation 0 or 1, it can be analog optical gate. It is normally called as a analog optical gate. So, between 0 and 1, any other values also we can get. Okay. So, now using that optical gate, universal optical gate, I will try to show some outline how one can demonstrate integrated photonic switch fabrics using building blocks. Major building blocks will be given, and how this universal 2x2 optical gate can be arranged in a certain fashion to get a photonic switch fabrics on chip, integrated photonic switch fabrics. And finally, the most interesting thing, that is called field programmable photonic gate array. Note that this is FPGA, not FPGA. FPGA is a field programmable gate array, that is used for electronics, digital electronics, for digital logic operation, that is also that is programmable also. But here also we will be just demonstrating, this is recently materialized, visualized and demonstrated also some certain circuits which can be called as a programmable photonic gate array, field programmable photonic gate array, that can be programmed for various types of functionalities. Of course, that is optical functionalities, which can be digital as well as analog also. Okay. FPGA in electronics is necessarily, it has to be digital logic, but in this case this FPGA, field programmable photonic gate array, that is mostly used for analog function, analog operations, analog photonic signal processing purpose. So, now let us try this universal 2x2 optical gate, how it is conceived. This is nothing but, if you just see the passive structure first, that this is a waveguide structure. It is like a 2x2 Mach-Zehnder interferometer. First you consider, and you see in this structure, that is a 2 3 dB power splitter, maybe directional coupler here, DC 2, DC 1, DC 1, they are just cascaded, and it is it is normally called as Mach-Zehnder interferometer, Mach-Zehnder interferometer 2x2 Mach-Zehnder interferometer. And the transfer function for this Mach-Zehnder interferometer we have derived earlier. I just reproduce here for completeness. This 3 dB power splitter, if I annote that input coming here in the port 1 AI, and another input can be fed at another input port, that is BI. That means this is the field amplitude. As you know, it is represented by A e to the power j omega t minus beta z. Beta is the propagation constant of the guided mode, and then also you should have field distribution also for the guided mode. So, this A whatever amplitude is depicted here, it is launched here, field profile for a single mode waveguide you can think, and that mode can have a phase propagation, that is omega t minus beta z, like that. Similarly, another field, another signal you can think of B I is here. So, in that case, if A I B I and here any field is coming out, that can be related using this transfer matrix. This is for a 3 dB power splitter. 3 dB power splitter, when directional coupler used as a 3 dB power splitter, the transfer matrix we have derived earlier, this is directly reproduced. Instead of that, I think it is better to represent A 1 B 1. This is B 1 and this should be A 2 B 2. Okay. That way it is better to explain. So, this is A 1 B 1 A 2 B 2, anything you can give, but in this expression what you see that is related to A I to A 1 B 1. This is A 1 and this is B 1, whatever field is coming here, that is related here. And if this is a balanced Mach-Zehnder interferometer, that means the length L 1 equal to L, L 2 equal to L, then when propagating through this length for this field, it will acquire certain phase, that e to the power minus j beta L we just put down here, and phi 2 also. It is basically phi 1 equal to beta L and phi 2 equal to beta L here. That means, normally the phase factor, it should mention as a phase factor. Then I can relate this A 2 B 2, A 2 B 2 in terms of A 1 B 1, that is like this. Okay. And then if you have a second directional coupler, that is related to output field here, output amplitude A 0 and B 0, that can be related to A 2 and B 2, like this. So, using all these expression, if I just consider, that is actually A 1 B 1, let us consider like this, correct it, and this is A 2 and B 2, like that. Then what we can get using this, for example, A 1 B 1 can be written from here. This is one matrix you can write here, and then whenever you are getting A 1 B 1, A I B I you are getting, and A 2 B 2 you can just write like this. So, A 2 B 2 equal to A 1 B 1 here. So, what you could do, instead of A 1 B 1, instead of A 1 B 1, you can write this one. Okay. Then ultimately using this, all these matrix you just multiply, then you can relate A 0 B 0 to A I B I. So, A 0 B 0 and A I B I you can relate. So, this is your transfer matrix. Okay. Fine. Now, if you just find the amplitude, what is A 0? A 0 will be this one, and what is B 0? B 0 from this you get this one. So, you are just launching A I here, this A I and here B I, this A I appear as a B 0 with some additional phase, the propagation phase factor, and then additional phase factor is just pi by 2. Similarly, whatever you are launching B I, that will appear in the cross port as a 0 B I with additional things. So, this is both of them will be in phase basically. If you launch here, whatever you get here, whatever phase you will be getting, you will launch here, here also you will be getting same phase. Basically, propagation, this arm length propagation constant, that is the phase e to the power minus j, you can say that beta L plus pi by 2, that is the phase you will be getting, but it will appear in the cross port, that we have discussed earlier. So, we conclude that complete transition to cross port with an additional phase shift of pi by 2. So, propagation constant, whatever propagation length dependent phase you are getting, that is there, but in addition to that, because of the directional coupler, it will be having another pi by 2 phase shift, that we know. This is we have discussed already before. So, you can think of, instead of this balanced Mach-Zehnder, okay, balanced arm, if you could think this 3 dB and this 3 dB DC, DC 1 and DC 2, if it is directly connected, that means you are doubling the directional coupler length. Obviously, this will be your B 1 this will be your A2, this is B2 according to the annotation, all these expression we have given. Okay. So, using this again what we can get, if this is missing for example, then whatever you supposed to get here, that is exactly like a cross directional coupler with cross coupling length. That is what, thus a balanced Mach-Zehnder interferometer, that is with phi 1 and phi 2, that phi 1 equal to phi 2 is equivalent to a DC with LDC equal to LC. So, if you have a directional coupler length LDC equal to LC, that means cross coupling length, then if you launch here it will directly appear in the cross port, and if you launch here it will directly appear in the bar port. So, this type of Mach-Zehnder interferometer, balanced Mach-Zehnder interferometer, if you operate passively, it is actually nothing but a simple directional coupler. Instead of two directional coupler cascaded with a gap, with a distance, with a certain waveguide in between, as if you can think that that is missing. If that is missing also, your functionality point of view, no difference. But we can use that this two arm in addition to this 2 3 dB power splitter to get advantage of some kind of integrating a phase shifter in these arms. So, you can integrate a phase shifter here, that can be actually isolated from the lower arm, and if you integrate a phase shifter here, this phase shifter can be isolated from the other arm, it will not affect the other arm. So, to get that advantage we use this type of thing. Suppose you have a phase shifter here, phase shifter here, phase shifter, and this is also phase shifter, that can be a thermo-optic heater, micro heater. Then if this is phi 1, this is phi 2 phase, additional phase is there. So, phase factor will add to the amplitude minus j phi 1 here, and here it will be adding minus j phi 2. Okay. So, in that case if you use this one A2 B2 and A1 B1 relationship here, right. So, this in this case A2 B2, this expression can insert here, and this A1 B1 can again insert here, then ultimately you can relate A naught B naught to AI B naught. That means, input to output you can relate with a 2 by 2 matrix here, transfer matrix. This is the transfer matrix of the so called Mach-Zehnder interferometer with additional phi 1 and phi 2 phase shifter in upper arms and lower arms respectively. This can be actively controlled, it can be tuned, phi 2 can be tuned, depending on the phi 1 and phi 2 you are supposed to get this type of matrix. So, this matrix little bit can be simplified. How that is? Let me try. So, what you do, this one you just multiply this factor, and every element you multiply with e to the power j phi 1 plus phi 2 by 2. So, minus, and then every element if you multiply this one, then you have to multiply minus j here. So, that is same. So, if you multiply this one, this term becomes like this. So, it was e to the power minus j phi 1, and if you multiply this term, then it will be becoming like this, phi 1 minus j phi 1 minus phi 2 by 2. And if you multiply this one with this one, this will be coming also phi 1 minus phi 2 by 2, but instead of minus here plus. Okay. Same way, if you multiply this one with this term, then you get this one. So, minus plus and additional minus j will be there, and this term also identical, if it, because this one and this one same, right. So, in that case you will get another term similar to diagonal terms are same, these two terms are same, and then this term if you multiply this one with this one, you get another one exactly like this with additional term minus. Okay. So, this is a now little bit modification. This modification is such that instead of phi 1 and phi 2 variable, we have now two variables. That is the trick, that mathematical trick we have used to get a particular type of mathematical simplification. So, we have instead of phi 1 phi 2, we have two variables phi 1 phi 2 and phi 1 plus phi 2 phi 1 minus phi 2. Okay. So, this is the expression for the transfer matrix. Now, you see this is the thing we have written. So, this one if you just expand, that means e to the power minus j theta, you can write cos theta plus minus j minus, it should be minus j theta, e to the power j theta can be e to the power cos theta plus j sin theta, de Moivre's theorem. So, if you use that, then what you get, this factor I leave it as it is, and this one it will be, you will be getting minus j 2 sin phi 1 minus phi 2 by 2, and this one would be minus j 2 cos phi 1 minus phi 2 by 2. So, sin cos function we have just established. Okay. So, we just introduce two different variable instead of phi 1 phi 2, they are sum of the phase and subtraction of the difference of the phase, that two variable we have introduced, and of course, divided by 2, that is it. Now, let us see, we just reproduced here. Now, what we do, we can take, you see, minus j 2 we can factor outside. So, if you do that, so what you get, and also you assume phi 1 plus phi 2 by 2 as a delta 1, phi 1 minus phi 2 as a delta 2. Okay. So, in that case I can have minus j 2 sin delta 2 minus j 2 cos delta 2, that is all. So, phi 1 phi 2 you are just substituting this, simple, straightforward. Then what you get, minus 2 j if you take out, then sin delta 2 cos delta 2, all the elements cos delta 2 minus sin delta 2. This is actually unitary operation. That means, if you have phi 1 and phi 2 whatever you get, but this matrix actually if you see determinant of that matrix, if you are calling that matrix as a x. So, determinant of x actually if you see sin square delta 2. So, this is actually minus 1, that means it is giving some minus pi phase shift, and as well as the amplitude is 1. So, such type of operation is called, if determinant is 1, that type of operation you are operating on this vector and then operating this matrix, then you are getting this matrix is actually unitary operation, that means unitary matrix, this matrix called unitary matrix. Okay. Unitary matrix, that unitary matrix actually of course, this is unitary when you are considering there is no loss in the structure. So, we are assuming that loss is negligibly small, and in that case you can get this unitary operation, and where all the power energy you are launching here, that will appear here without any loss. And this thing you see additional phase will be there, that is common to both the arm A naught and B naught, that we can actually define like this. So, we have reproduced same thing like previous slide, and then you see what is A naught? A naught is this one and B naught is this one after unitary operation. So, that is why it is called universal 2 by 2 optical gate, and why it is optical gate, that will be revealed quickly. Okay. So, if you understood up to this point, it is easy for you. Okay. Next forward, let us see why it is called universal 2 by 2 optical gate, because this type of 2 by 2, this is a gate. First of all, why this would be called as a gate? For B I equal to, just think about that B I equal to 0, for example, assume you have without B I equal to 0, you have this A naught will be this one, B naught will be this one, whatever you are supposed to get. So, now once you disable this one, then this one will go, this one will go. That means, A naught will be A I sin delta 2 times e to the power minus j delta 1, and then minus j will give you minus j pi by 2. Okay. This is the phase factor, okay. And this is your amplitude, and this is your phase, and here also in B naught this is your amplitude, and this is your phase factor. So, now you imagine this device, very interesting device. Why? If you just change delta 2, then you can change amplitude at the, suppose this is input here, this will be called as a bar port. In the bar port, amplitude varies as delta 2. What is delta 2? This one. So, amplitude can be varied by the factor of phase difference between the two arms. So, if you maintain certain kind of phase difference, then you can actually control the amplitude whatever you are getting here. Okay. Now, phase, how much phase you want, that is actually decided by delta 1. So, if you can tune this one, then you can actually control tune. If you can program phi 1 phi 2 can be tuned, so that you can tune the phase without disturbing. So, phi 1 phi 2, phi 1 plus phi 2 you tune such that phi 1 minus phi 2 is constant. When phi 1 minus phi 2 is constant, amplitude remain constant, and in that case your phase will be changed. So, by controlling delta 1 and delta 2, you can control here both amplitude and phase independently. Similar case is for B naught. So, delta 2 actually can control your amplitude and delta 1 can control your phase. For example, if you are considering, suppose phi 1 equal to phi 2 for example. So, that means, if I am whatever phase I am giving here, same phase I am giving here. So, in that case what happens? This one will be delta 2 will be equal to 0, delta 2 will be equal to 0, right. So, delta 2 equal to 0 means this one will be equal to 0, BIU is not there. So, at the bar port you get 0 amplitude, but in the cross port you can get maximum cos delta 2 equal to 0 equal to, if you are putting 0 1. So, that will be like a simple thing, that is actually whatever established before, right. And if you are just changing phi 1 and phi 2 equally, so equally you are changing, this is 0, but this value is not going to be 0, that will be something phi 1 equal to phi 2 may be equal to phi. So, delta 1 will be equal to phi. So, that means whatever phase you are giving, that phase will appear here. So, it will be coming here, this whenever you are launching here, that will be coming here as a output, but both phase if you are equally changing phi 1 equal to phi 2, then that phase will be introduced here. So, it will be just phase can be modulated, phase can be tuned. So, now what we have established that by integrating two phase shifter, thermo-optic phase shifter, we can program that. By programming that, at the output I can control both amplitude as well as phase. So, this is a very nice device, and you can use that as a building block for large integrated circuits. Okay. That is why it is called tunable basic unit. How that is that can be used as a basic building block for large scale integrated circuit, we will be discussing in later slides, but here you just consider why it is called tunable, because both amplitude and phase can be tuned, nothing to do with the wavelength, we are considering same lambda operation. Okay. So, any lambda you operate here, all these derivations that will stand. So, that is why it is called a optical gate, and this in this optical gate you are not expecting only digital data 0 or 1, any amplitude you can get, any phase you can get. So, that is why it is called analog optical gate. So, it is not just to distinguish the electronic gate normally when we define that is actually digital gate, but here we will call whenever optical gate is there, that is basically analog optical gate. So, you can completely disable power here, if you launch here you can bring here just by controlling phi 1 and phi 2, and fraction of power here and fraction and rest of the power here, that is also controlling by phi 1 by phi 2, and their phase can be also detuned. So, now what? So, this is the conclusion, both amplitude phase can be detuned and programmed using a pair of phase shifters in the balanced MZI. That is just a take home message. But after getting this, how you can utilize this is a nice device, this is giving you a unitary operation for these inputs, 2 inputs and 2 output, you are getting a unitary operation, fantastic, and also any of the output ports you can control your amplitude and phase at your will by adjusting phi 1 and phi 2. right. How that can be done? You need to have a design, you have to design a driver, electronic device, because you will need a program. Suppose you want here, suppose you need amplitude maybe 0.5 and phase maybe pi by 2. Okay. For that you have to compute what phi 1 and phi 2 combination you need, and that combination can be supplied by a electronic driver. So, electronic driver can actually control the signal from port 1, port 2 input ports to port 1 and port 2 output ports, here we are considering. But thing is that you can have an optical signal which is modulated, some data can be encoded, that can be analog data, that can be digital data. So, that data we represent as a signal, time dependent amplitude variation is there. Irrespective of the time variations here A to B, Bt, whatever the data you are getting, you can actually sync your electronic driver. Accordingly, you can change your path from this to this. You can have this A signal partly in Ct and partly in Dt, B signal also partly in Ct, partly in Dt also. So, you can mix any combination of these two signal for at any instant of time by programming this electronic driver circuit. Here is a good example, a very recently published paper by Bogers et al., and that is published in Nature journal, that is called Programmable photonic circuits. That is the latest trend. So far all the photonic integrated circuits used, they are actually application specific. That means a particular circuit you can use for a particular function. Now, if you can somehow program your optical gate, then you can actually route your signal to different path, and you can actually feed output of one signal to multiple device at the multiple device, so that you can get different functions using this whatever so called tunable basic unit. Okay. So, here it is nicely a perspective pictures given. Suppose you have a signal coming here and this is 2 input waveguide, and this can be a Mach-Zehnder interferometer, or maybe simply we can consider this whatever signal comes here, kappa fraction can of the power, kappa fraction of the power can be coupled to the cross port, and 1 minus kappa power can go to the bar port, right. So, square root whenever kappa is there, that can be considered as a intensity coupling coefficient, 1 minus kappa is the intensity or power coupling coefficient, square root if you use, that will be amplitude coupling coefficient to this path and this path. And correspondingly, as we have established earlier, the matrix, whatever the transfer matrix, which is unitary transfer matrix, it is written in a different form, but it is same basically. So, you can get this B1 and B2, A1, A2, and it is missing that it can be time dependent, it can be time dependent signal, it can be time dependent signal, it can be time dependent signal. Okay. So, this is actually can be represented, and pictorially it is shown here, that signal coming here, it can go directly this path and this path. If you are putting like this, you can program such that this will only go to bar port, and whenever you are putting here, that also will only go to bar port. And you can program again, you can actually change your phi 1, phi 2 as discussed before, such that this power completely goes to cross port and this can completely goes to cross port. They change their path route. But you can also program partial. So, something goes here and something comes here. Similarly, whatever you are giving here, something here. So, that is why it is this type of situation, you can say that it is actually like a digital type on off situation is happening. So, whenever you are going there, that signal is missing here, but something coming here, that will be coming here, that will be missing here. But here you can get any amplitude, you can split maybe 10% here, 90% here, maybe 20% here, 80% here. So, any amount of fraction, a power splitting ratio, you can control program using whatever we have discussed so far, tunable basic unit or universal 2 by 2 optical gate. So, this is the different way of phase shifter integration, it is shown here. Actually, you can use a simple Mach-Zehnder, only one phase shifter here and another phase shifter instead of both arms, you can have phase shifter at the other arm. So, you can actually control phase as well as amplitude at the both the output by controlling this P1 and P2. This one I have explained in the previous slides, okay. And this one sometimes instead of going for, so go back to the previous slide, it will be clear. Instead of just controlling amplitude here, you can think of just simple one directional coupler. You know directional coupler, you can design like LC. This is LC. So, if you launch here, normally everything should be coming here, and if you launch here, everything should be coming here. But what you could do, you can have a phase shifter here. This phase shifter, it can be thermo-optic phase shifter, which can actually affect more to the closest waveguide compared to the farthest waveguide. So, if you just control this, control the phase of one of the coupled waveguide, then you can actually control amplitude as well as phase at the output. So, but normally it is very challenging task. If you just two parallel waveguide and if you put a heater, the parallel waveguide, their separation is hardly 100 nanometer to 200 nanometer. So, if you heat one of the waveguide, automatically it will be hitting the other waveguide. So, it is very much expensive and design cost is very high and complicated design of course. So, that you can insulate one waveguide to another waveguide. When you are hitting one of the waveguide, coupled waveguide, other waveguide remain insulated, that is very difficult. So, most of the time people use this type of tunable basic unit, so that you can avoid this type of complicated design. However, if you are using this type of building block or this type of building block, relatively your footprint will be large. Okay. So far the compact design of any tunable basic building block or tunable basic unit so far demonstrated for unitary operation or universal 2x2 optical gate in the order of more than something like that, in the order of 500 micrometer. Okay. So, that it can be really considered close to unitary operation, losses etcetera can be negligibly small. Okay. Fine. So, this is what recently published in 2020. So, that now people already, you can imagine that people started using this type of basic unit, tunable basic unit or TBUs or universal 2x2 optical gate for large scale integrated circuit for field programmable gate array. Before going into the field programmable gate array, we just want to discuss the technology. What type of technology and what type of building block? Is that the Mach-Zehnder interferometer can be considered as the only choice of tunable basic unit? For example, directional coupler, if it is designed, that can be also possible. There are many different ways of design people are considering, so that compactness can be succeeded, so that footprint can be lower, because you want to use this type of optical gate for large scale programmable circuits, integrated programmable circuits. So, compactness is very much important. That is the reason people also, but that design should be such that it should be compatible to CMOS fabrication technology, CMOS compatible fabrication technology. So, normally to this type of programmable circuits or tunable basic unit or 2x2 optical gate, they are materialized by integrating a thermo-optic phase shifter, as I mentioned. Thermo-optic phase shifter we have discussed earlier. So, that type of thermo-optic phase shifter one can have, this is your substrate, silicon substrate, you can define your silicon and you can have electronics in this layer, in the device layer, but you can have in between, you can have a oxide, and top of the oxide you can have a heater. This is your heater, this is your micro heater, and then you can have a bias where you are actually V plus V minus, so that current can flow in this direction, and then you can have a I square R, and then Joule heating effect that will actually transfer the energy to the silicon, and then because of the thermo-optic effect dN effective by dt, that is actually in the order of 2 into 10 to the power minus 4 per Kelvin. So, that type of refractive index change, and then this refractive index change can be, if delta T temperature, then the delta N effective by dt, delta T and time delta T, and then this delta N in eventually it can change the phase shift, that is nothing but 2 pi by lambda delta N times L path length. But this type of phase shifter, it is called BEOL phase shifter. BEOL stands for back end of the line. So, back end of the line process means, this line process means it is a CMOS process, and back end normally after fabrication, whenever you are fabricating, defining your waveguide structure, different type of active elements, electronics, etc., that is actually called front end process. So, front end, after front end process line, everything completed, in the back of the process line, that is why it is called back end of the line, you can integrate the phase shifter, that is why it is called BEOL phase shifter. But sometimes you can have also in the phase shifter can be integrated in the front end of the line, FUL, front end of the line. Okay, front end of the line. Front end of the line means you can have a reef type of structure, and some region you can dope a bit, so that your conductivity can be increased. Normally silicon waveguide, when you fabricate, typically they are intrinsic, concentration is in the less than 10 to the power 15 per centimeter cube or so. Okay. But whenever you would, that means conductivity is very poor, but if you little bit dope here, so that conductivity high, and then you can make a contact pad and you can send a current. So, here you can have I square R, and then this heat can be transferred directly to the silicon waveguide, because you have a conducting path also, thermal conducting path also there. So, you can get a phase shifter. So, this type of phase shifter are also very popular. Sometimes we have found that this type of phase shifter is having power consumption, power ratings, that means figure of merits is much better than this type of phase shifter. So, one can also define front end of the line phase shifters. Only thing is that you have additional process which is very costly process, that is actually N plus implantation, but that is a part of CMOS technology, that should not be a problem. And another type of phase shifter also people realize, you know, instead of that is also front end phase shifter. How that is? You have silicon waveguide in the center, one side it is N doping, another side is P doping. Okay. Now, if you bias in between, this is something like that, this is kind of N I P device diode. In this cross section, if you see N doping, intrinsic and P. So, it is basically a diode, pin diode type thing. If you read from this side, it is a pin diode. If you are giving forward bias, what happens? Then the carrier, this hole will be injected to this side, and here electron will be injected to this side. And whenever withdraw the bias, forward bias, then carrier will be again returned back again, it will be depleted from the waveguide region. Now, we will be showing that by controlling this carrier concentration N, delta N or delta P, if you can control, if you can just increase or decrease by controlling the free carrier, you can also change the refractive index. That actually is possible for phase shifter, reasonable amount of phase shifter you can, if you can just carrier concentration, if you can vary in the order of something 10 to the power 18 to 10 to the power 19 carrier concentration, you can get the refractive index change in the order of 10 to the power minus 4, which is actually equivalent to your thermal refractive index change. So, that refractive index change also you can get, and you can get a phase shifter, and that also you can integrate in the front end of the line. Okay. So, this type of phase shifter you can do, and it is shown here basic building block in this paper actually. This is recently published also in 2019 in Journal of Light Wave Technology by B.G. Lee and Dupuis, silicon photonic switch fabrics, and they have used all the, they have compared all these three types of phase shifters and their figure of merits etc. controlled, and they have shown that using this phase shifter you can realize a Mach-Zehnder interferometer, where this time dependent phase it can be 0 or pi for digital application, right. You can have phi 0, and you can have another arm where you can actually give certain kind of bias to compensate if there is any type of phase difference is there after fabrication, post fabrication etc. you can do that. and at the same time this is actually TBU. You can consider this is a tunable basic unit or 2 by 2 optical gate. Another 2 by 2 optical gate can be demonstrated, here it is explained nicely, that is with a ring resonator. You see, this is a ring resonator and one waveguide you can consider, this is input and another waveguide, bus waveguide here connected here, and that is another input you can consider. One input here, another input here, and you can access here and here. Okay. So, 2 input ports and 2 output ports. The problem is that in this type of structure 2 input ports are in one side and 2 output ports in the right side, but in this case both side input ports are there, one side input port and another side input port. So, whenever you are launching something here, if it is resonant wavelength, it will be coupled here and it will keep on circulating here, and then part of it while circulating it can go here, output here. Okay. Part of it will go here as it circulate here. So, part of it will go here, and when it is circulated it is coupled and coming back, then part of it will go here also. Now, whenever you are launching here, that same situation, it will go here, if it is resonant it will be coupled here, it will be stored here and it will be coming here, and part of it goes here, again goes here. So, it is actually a representation of 2 by 2. Only thing is that your operating wavelength you are using here, that should be resonant to the ring. If it is off resonant, then you can control the phase here, bias here, so that that particular wavelength can be also resonant to the micro ring resonator. So, by controlling phase in one of the arm here, you can actually adjust the operating wavelength, and by controlling another phase shift you can actually make the device for digital operation, phi 1 t can be 0 or phi 0, anything, any phase you can consider, and you can control the power coming out here and coming out here. Same fashion you can show that both output amplitude can be detuned by amplitude can be detuned as well as phase can be also detuned. So, it can be also considered as a TBU. However, because it is a resonant device very much sensitive to lambda etc. So, relatively difficult to implement. However, footprint for a ring resonator based TBU will be smaller, relatively smaller compared to footprint of the Mach-Zehnder interferometer based, because this ring resonator can be as small as 10 micrometer things. And however, the phase shifter if you want to introduce a reasonable amount of phase, that if it is thermal phase shifter, that means your temperature rise will be very high, which is actually not so desirable. That is the reason, to control the temperature, instead of thermoptic phase shifter, one can go for this type of phase shifter. It is called plasma dispersion effect. That means carrier concentration you are controlling, free carrier concentration, and by that means you can control the refractive index, and forward bias you can use, so that you can have your phase control, plasma dispersion based phase control. I will be discussing little more detail this one when we will be discussing high speed modulator, because in high speed modulator also same configuration it is used, but instead of forward bias there we have to give reverse bias, so that high speed switching can be done. For modulator high speed modulation purpose, you need high speed carrier drifting away from the core of the waveguide. So, that I will be discussing in the next class in detail how this refractive index change happens, how it is dependent on free carrier and wavelength dependencies etc. we will be discussing, and how that can be translated into demonstrating different type of photonic integrated photonic modulator in silicon photonics platform, right. So, this is the TBU, as I mentioned that this TBU can be used, Mach-Zehnder interferometer, 2 by 2 Mach-Zehnder interferometer, that is a perfect thing, but one can also try for compactness purpose a micro ring resonator based TBU also, but which is very much lambda sensitive. Good. Now, here one example, again this taken from this paper Nature, they have actually shown that how a integrated photonic switch fabrics can be demonstrated. For example, you have, instead of 2 by 2 ports, you can have multiple input ports 1, 2, 3, 4, 5, and you have multiple output ports 1, 2, 3, 4, 5, and they are cascaded with Mach-Zehnder interferometer. You see, this is called Mach-Zehnder interferometer 1,4. Why it is 1,4 we will be explaining a little while later. This Mach-Zehnder interferometer 1,3, that means first number representing the input port and second number it is routing to port 4. Okay. This is actually that is how they have indexed in the paper. And you see one of the port it is going like this and another output port it is coming through that, but in between you have a D14, one device is there. That device normally it is very difficult to implement though, but they have demonstrated that it is called actually transparent photodetector. You can detect how much power in this arm, but it will not lose any power, power will go, most of the power will come to the next Mach-Zehnder interferometer. So, all this Mach-Zehnder interferometer is tunable, you can control phase and amplitude everywhere. Okay. And how much power, because of the programming purpose you are controlling your phi 1 and phi 2 in each of these Mach-Zehnder interferometer, right. So, that amplitude and phase can be there, that can be detected by transparent detector D14, D13, D12 actually tactfully placed, so that you can find how much power it is transmitting, so that you can train the entire circuit that okay, if I have to set phi 1 equal to this one and phi 2 equal to this one for a set of amplitude this one and phase this one. So, that for training purpose this type of integrated photonic photodetectors also require, and this is actually triangular shaped unitary operation, cascaded diagonal line, that is actually triangular unitary operation. You see this is actually you are launching here and light will this will be activated like that, so that it can 5 to 1 it can go. So, you can just activate that to operate certain set of Mach-Zehnder interferometer with certain set of biasing, so that certain set of output port. Even if you are launching here, you can get any of the output ports 1, 2, 3, 4 or 5 anywhere you can choose. So, some other microphotograph shown for different type of switch fabrics, where you can have, for example, here you can see that you can have a mode scrambler and diagonal line 1, diagonal line 2, that means this thing it is shown here, these three things, this operation it is shown here, and with some lines shown here for control electronics, control lines, that kind of metal lines will be there, so that all the bias can be controlled to different phase shifters. And this is another one where it is shown that there are 240 control lines, because multiple TBU, tunable basic unit or Mach-Zehnder interferometer is cascaded to get a switch fabric, so that you can get you can route your signal in different direction, and you can mix your signal for different applications also. Okay. So, you can see this type of chip they have demonstrated, that is in 2020 paper, this scale is 500 micrometers. So, entire chip may be in the order of maybe 2-3 millimeter or so length. So, it is a millimeter size chip. So, some other type of operation it is shown here, you have 4 input ports, but only 1 output ports you need. Here 4 by 4 again, but with a different set of activation. Mach-Zehnder interferometer actually rectangular unitary, this is called triangular unitary operation, and this is rectangular unitary operation. You see all the things actually the path actually it is showing like rectangular path, it is means all these things you are arranged in a this way. For example, 5 it is going here, so you have to activate all these things like this to going there. But here in this case you do not need that all these diagonal things or triangular path needed, you can just activate depending on the color code etc. you can get, that is actually programming part. Okay. So, that programming how one can do. Here it is a nice example again I have taken from this 2019 paper, where actually you see this is your so called this green color dashed line within this is called photonic switch module. And in this switch modules what all things are there? First thing is that you have a switch fabric, that is what discussed previously, you can n number of input and number of output, and in the input side you can have optical input that can be fibers, these are fibers, optical fibers, single mode fibers, and then you can have a input side certain kind of block called optical signal conditioning, because you know whenever optical signal coming through a fiber, it can be coming from long haul communication, right, long haul fiber bringing signals, and those signals can have certain polarization and certain dispersion things are there, but your switch fabrics they are fabricated, for example, using CMOS technology in silicon photonics. It cannot handle arbitrary polarization. It is a kind of polarization dependent circuit, and certain dispersion it may give you some adverse effect in switching. So, that is why you can all these things, whatever the dispersion, polarization, etc., that can be adjusted here in this block with different type of application specific photonic integrated circuit, and that is why it is called optical signal conditioning. And then all these input ports, again you are coming here and you operate with unitary operation, so called unitary operation, that can be switching fabric, that can be interferometric operation, so on, and then whatever output here coming, again you can give it to any of the output ports. And before feeding into another channel, another fiber, you can have another optical signal conditioning block. You can anything distorted here, signal, etc., you can just process it, treat it, and you can send it to another ports. But in this switch fabric, what you need? You need a state control logic, you need a bias control logic, sometimes you need a bias and sometimes logic control. This can be digital control circuit, digital data is coming here, and you can feed into different control line, different TBUs you can give. Bias also can go to different TBUs, and sometimes data read in processing, receiver amplifier. Sometimes in the before you send it to you have to check, for example, you need in this case you have some kind of transparent detector. That detector signal, it will see, it can read the signal whether power is right or not in that branch. That power you can read, and based on that you can give it to the feedback control here. So, that control logic will automatically adjust your bias, all those type of things. Bias can be also changed. Suppose power is fluctuated a bit. So, this detection unit, it will give some feedback to the bias control unit, so that it can readjust your bias such that power level can be adjusted. So, this is for control loop. So, all these electronics, so called driver circuit, that actually will have logic, digital signal, that can be time dependent signal can come here, and some signal you can give that signal bias controlling purpose for different things, and something for receiver and giving some feedback control. So, all these electronics, they are actually well known, they are normally used in electronic circuit for decades, and you can use that type of the self FPGA, for example, field programmable gate array, or you can design your driver circuit according to the standard PDKs, and you can co-integrate with the photonics switch circuit in silicon, and then you can have intercontrol. So, optical input to output, you can just optical signal processing purpose you can use. So, this is the whole architecture for operating photonics chip in the name of photonic switch fabrics here, but it need not be just a switching fabric, it can be some other functionalities. For example, some kind of computation chip, photonic computation chip, silicon photonics computation chip, quantum photonic chip, I would say. So, those type of thing I will be just giving some example maybe later if time permits. So, that also can be designed, that can be controlled with a different type of TBUs and tunable basic unit and unitary operations, and that can be, that driver circuit also can be co-integrated. Okay. Now, the final thing, field programmable photonic gate array. So, you have the TBU, tunable basic unit, for 2 by 2 optical gate operation as a MZI, and can be ring resonator, optical gate, 2 by 2 optical gate. Okay. That is basically MZI or micro ring resonator as discussed. And these TBUs, we have shown that how that can be used for a switch fabric, people demonstrated already, and you can control program that TBU, individual TBU you can program to get a certain type of output. Now, we know that FPGA, field in electronics domain, FPGA, field programmable gate array. So, you have some ASIC circuit, application specific circuit in electronics, and that ASIC circuit actually it is sometimes you may need a different type of application, different type of circuit. Instead of that, people thought that if some circuit you can design, you can actually program that for different application, then your cost and footprint, everything, and lot of functionality, additional things you can get also advantage. So, that thing is that they are actually FPGA, you have logic gates, individual logic gates, you just arrange in a certain fashion, you can make certain circuits, so that you can actually configure them using Verilog program and different other type of programs are there, and then you can reconfigure that one for different functions. So, people thought that if it is possible for electronic domain, for electronic functionality, maybe you can also have similar type of approach for photonics functionality, for photonic signal processing. But remember that photonic signal processing, people want analog processing, but FPGA it is like a digital processing. So, people thought that a structure, for example, like this, you can think of TBUs, it can be arranged like in a square mesh, or you can arrange like a hexagonal mesh, or you can arrange like a triangular mesh. So, if you see, it is a 2 input 2 output, that 2 input output goes here, and it can be connected, one goes to one MZI and another input comes from another MZI. So, in this way it is connected. So, this is a MZI unit, these are all MZI unit. So, you can arrange in a square mesh. So, this individual MZI is called it is a individual gate, 2 by 2 optical gate, and they are actually arranged in a square mesh, and that can be also arranged in a this TBUs can be arranged in a hexagonal mesh. Like you see 6 MZI is required to complete a hexagon. You know, the hexagon is a very compact design, but thing is that for making a one round ring type of resonator type of architecture, you have to pass through 6 different TBUs. But in this case, if you want to get a round trip circulation resonance type of things, then you need to pass through only 4 TBUs. And you can have also triangular shape also. In the triangular shape, one disadvantage is that this area, this footprint is unnecessarily wasting. Okay? And here in this case, you do not have wasting when you are connecting to different TBUs. Here also, whenever you are connecting, some kind of wasting is there, but in case of hexagonal design architecture, you are not wasting at all. So, this type of 2 by 2 unitary optical gate you can arrange, and then you can program each of these TBUs so that you can route your signal in a certain path, such that if you are just circulating the signal only in this path, then you can get certain kind of ring resonator operation. And you can also think of that this ring and this ring can be activated, so that you can have a coupled ring, this type of ring resonator coupled with this type of ring resonator. Also this resonator can be coupled also. So, coupled ring resonator you can get. Also you can have cascaded, for example, you want to cascade certain Mach-Zehnder interval, you cascade this one and this one, and then you can go this one, you do not need to activate this one, you can cascade this one, and then you can keep, you can have also delay line also, delay path. You can, as much as you want, you can actually route the signal according to your requirement. So, you can have a delay line, you can have a cascaded interferometer, MZI based interferometer, you can have a coupled ring resonators. All these things you can use, coupled ring resonators or cascaded interferometers you can use for various type of interference experiment performance, as well as different type of what do you call that, delay lines, filter characteristics, all those type of operations you can have. Here some of the fabricated device shown here, and they have demonstrated basically Boger Settle, and particularly this Kapmani group in University of Valencia, they designed and they fabricated, and their results shown here. For example, by programming this type of hexagonal mesh structure, they could actually demonstrate different type of filter characteristics, ring resonator filter characteristics, either this one or this one, different order, first order filter, second order filter, third order filter. They can demonstrate by coupling one basic filter unit to another filter unit, cascading those type of things they have demonstrated. So, this is why it is called field programming photonic gate array. You can every field you can independently you can program to get a certain type of functionalities. It is like each of them like a logic gate, but optical logic gate which can be used as an analog function purpose, but FPGA in electronics domain that can be used for a digital electronics operation purpose. But remember that this FPGA, it is just for photonic signal processing and FPGA for electronic signal processing. So, the purpose for FPGA is different and purpose for FPGA is completely different. It is not that this FPGA is going to replace FPGA. FPGA has a different function. Rather, it is interesting to see that this FPGA, field programmable photonic gate array, this type of architectures for different type of operation, different type of functions, to control them, to program them, people use FPGA. Control electronics is normally is designed using FPGA circuit. Okay. So, FPGA is a component for FPGA operations. So, FPGA is not to replace FPGA. Normally people always think that okay, photonic circuit it can replace electronic circuit. As I always mention that it is not true. Photonics is actually complementing electronics, where electronics failed or cannot be improved, the performance cannot be improved, there some of the functionalities you can replace by photonic counterpart. Okay. So, this is one of the area recently being opened and it is going to go very long way, because you can design a particular circuit, you can fabricate a circuit and that can be reconfigured for various functionalities, including microwave signal processing to microwave photonic signal processing to quantum photonic processing, quantum information processing, all those type of thing can be done. And here is a particular how you can do it, and there is a pictorial it is shown here on the same paper. So, you have a FPGA unit and this is actually programmable part, that means FPGA part, and you can have some devices like high speed phase modulators. I will be discussing that. They are application specific device you can have, and some of the block you can assign, those are specialized functional optical blocks you can have, which you cannot actually realize using your field programmable gate array. You can just whenever necessary you can access them. And laser, of course, silicon you cannot integrate laser can be off chip, right. So, your RF input, for example, in this case you have the for example RF signal coming, RF signal is modulated with the optical signal, and then this thing can be coming as a input, and then this input you can process with the optical signals, and all these TBUs, optical gates, they can be controlled by a electronics, right. That electronic circuit can be off chip. This is for example here electronics is here, this is your FPGA, and all the RF signal can come here, RF signal can be output here. So, both side input output RF signal, and optical signals can come here, these are the optical lines, and you can interface that with a computer. So, your electronics can be programmed, and according to that program, that is driver electronics can be programmed, and according to the program signal will go to individual TBUs, and you can route your signals, amplitude, phase, you can just change according to your requirement, and then you get a particular functionalities for different applications. Okay. So, I close this for this lecture today. So, this is an important, I mean to say that this particular area is just recent, and you may not find anything in the textbook. So, you have to rely on all the material you have to collect from literature recently published, for example, this Nature paper, this paper, and also I recommend you to read also this paper also by this is a very nice paper, Switch Fabrics Technology and Architecture, and that other paper for field programmable gate array or programmable photonics nature paper. That will give you lot of insights whatever I discussed, and many more, much more you can learn from that paper. Thank you very much.